In this example problem, we'll look at how to find electric fields and then electric forces from those fields. So the problem asks us to find the electric field at B, and then based on that electric field at B, find the force on the particle at B. So let's first reproduce this diagram. We have A, we have B, and we have C. So we have point A, and at point A there is a positive charge that has an amount of Q, and then D away we have point B, and B is home to a negative charge with an amount of minus Q, and then at point C we have also a negative charge, and the amount of charge there is Q as well. So between point A and B we have a distance D, and then between B and C we have a distance D. All right, so the first task we're given is to find the electric field at point B, where this negative charge is located. So if we're finding the electric field, the first thing we want to do is take away the charge that is there, because the charge that is there does not determine the electric field at that point. It's the other charges that do. Take away that charge, and we will replace it with a small positive test charge. So if we once again reproduce this diagram, we have A, which is a positive, we have a positive charge here at A plus Q, and then at location B I'm going to take away the charge that is there, and then at location C we have this negative Q charge, and between points B and C we have a distance D, and then also here as well. So to find, first off, I'll find the direction of the electric field at B because of these other two charges. So to find the direction, I replace this charge that was there with a small positive test charge. And I ask the question, what direction is the force that each one of these other two charges would exert on this small positive test charge? So first off, charge A. Charge A is positive, my test charge is positive, and so the test charge would be repelled by A. So that means the electric field at location B, the electric field due to A points towards the right. It points in the positive X direction. Then I look at C and ask the question, what direction would the force be from C acting on my test charge? The test charge is positive, C is negative, so then the force would be to the right as well. This positive test charge would be attracted towards this negative charge. So that means the electric field produced that acts here, that is produced by C, is also in the positive X direction. So those are the directions of the electric fields made by A and made by C acting at location B. So since they're in the exact same direction, that tells me that eventually I'm just going to be able to add these two force vectors together, and it should be fairly simple. So next I need to figure out magnitude. How much electric field do I get from charge A? How much electric field do I get from charge B or from charge C at location B? So the electric field amount from charge A at this position at B is going to be equal to Ke times the amount of charge at A, which is Q, divided by the distance between charge A and the location where I'm finding the electric field, which is D squared. Because, just to remind ourselves, the electric field amount is equal to Ke times the amount of charge, and this is the charge that's not at the location where we're finding the electric field, but it's the other one, over R squared. So that's the electric field that is made by charge A at this location. Also, the amount of electric field made by charge C at location B is going to be equal to Ke. the amount of charge at C is also Q. It's negative, but I just use the amount of charge to find the magnitude of the electric field. I use the test charge to find the direction. So this is also going to be Q. And the distance between B and C, the location of the charge and the location of where I'm finding the electric field, that is also equal to D. And so that gets squared. So since these vectors are both pointing in the exact same direction, I can just add them up. And so the net electric field that is acting at location B would be the sum of these two electric fields, KEQ over D squared plus KEQ over D squared. Well, they're the same thing. I have two of them, so that's 2 KEQ over D squared. And then I also need to worry about the direction. Both of these are to the right. I sum them, I get something that's to the right, or the positive X direction. So that is my net electric field. It would also be to the right. So then the next question is, what is the force on the particle at B? So now I have my electric field, and to find the force on the particle, I put it back. I put it back at that location. So let's say that this is my net electric field vector. So this is E net. I put the charge back at that location where it's acting, and so this is location B, and B was negative. It had a charge of minus Q. So the force that acts on charge B, so that force acting on charge B, that net force, is going to be equal to the charge, the amount of, or the charge, including the sign, minus Q times the net electric field, E net, that acts at location B. So this was my net electric field, and it was in the positive X direction. The fact that I have a negative particle there means that the force actually points in the opposite direction. So this would be the force acting on particle B. I can tell it's opposite because the charge that I'm putting there is negative. So overall, I'd have to take minus Q and multiply by the magnitude of the net electric field. So that's 2 KEQ over D squared. And so I get an amount that is equal to 2 KEQ squared, I have a Q here and a Q here, over D squared, and then the direction would be in the negative X direction. So there's the vector magnitude for the force, and the force acts in the negative X direction. Last of all, I want to know, what is the force on particle C? So let's do this whole process again for particle C. So to do that, I would write down, here's my A, just reproducing that diagram. It's positive charge A. I leave the charge at B now because it's going to be making an electric field at location C. So there's B. B is a negative Q. And then at location C, I take away the charge there. And to find the direction of the electric field acting at point C, I put in a small positive test charge at that location. So these other two charges, charge A and charge B, are each creating electric field at location C. And I need to find the magnitude and the direction of those electric fields. So let's think about what each one of these charges is going to do to this positive test charge in order to find the direction of those electric fields. So first off, for A is positive. The test charge is positive, so A will be repelling the test charge. So that means the electric field made by A is going to be to the right in the positive X direction. What about the charge at B? Well, the charge at B is negative. The test charge is positive. The test charge will be attracted to the charge at B, and so the electric field made by charge B is going to be in the opposite direction. So it's going to be in the minus X direction. Okay, so the next thing to do is to figure out what are the magnitudes of these two electric fields. Let's start with A. So the electric field made by charge A is going to be KE. The amount of charge is Q. and then the distance between A and the point where I'm finding the electric field made by A at this location, that distance is actually 2d. And then that gets squared because this distance is d and then this distance is d. So C is 2d away from A. All right, so that's the electric field made by A at the location of C. So then I also need to find the electric field produced by charge B. So that's going to be Ke. The amount of charge at B is Q. And then the distance between B and C is d, and then that gets squared. So now if I want to find the net electric field, these two electric field vectors are pointing in the opposite direction. So I have this electric field vector that points in the positive x direction, and then this electric field vector that points in the negative x direction. So the net amount of electric field would be Keq over, and I'm going to just take this 2 and multiply it over the parentheses. So that would be 2 squared, which is 4, and then d squared, Keq over 4d squared, so that's this one. And then minus, since this second vector is pointed in the negative x direction, Keq over d squared. So if I want to simplify this a little bit, what I can do is I can actually factor out a Keq over d squared from each one of these two terms. If I do that, here Keq over d squared multiplies a 1/4, and then here there is just 1. So 1/4 minus 1 is -3/4. So I get a -3/4 Keq over d squared. So the amount of electric field is 3/4 Keq over d squared, and the electric field overall points in the negative x direction because this electric field vector is actually stronger. Both charges have the same amount of charge, but the one at B is closer, so it ends up winning. And so I would say that my net electric field at location C is equal to 3/4 Keq over d squared, and it acts in the negative x direction. So that net electric field is going to point in the negative x direction. So there's my E net. And then if I want to find the force on particle C, I put particle C back at the location of C and calculate the force. So if I put that particle back, that is a negative particle. It has an amount of charge equal to -q. And so then the force is equal to the charge, which is -q, times the strength of, or times the electric field. And the electric field is, as we found here, it's going in the negative x direction. So I'll put in a -3/4 Keq over d squared. So overall, I get 3/4 Keq squared over d squared. And this force is going in the positive x direction. And I can see that also from the fact that the net electric field is in the -x direction. I'm putting a negative particle there, so that means the force on that particle is going to be in the positive x direction. So if you have a negative particle, the force is always in the opposite direction to the electric field at that point.